Is this?
Yeah.
I feel like it was, okay. All right, there we go. Okay, so this is Dave Jewitt. So I'll just give you the basic background. He got his PhD from Caltech, and then he then became a professor at MIT, and then he moved on shortly after that to Hawaii, where he spent about 20 years. And for the last 5 years, he's been at UCLA, where he is a professor and also founded the UCLA Institute for Plants and Exoplanets. So I guess, so I was his PhD student in Hawaii, and I guess especially for the students in the audience, I'm supposed to say something about Dave as a scientist or a person or something, try to give you some secrets to how to become Dave or something like that. You know. I'm not sure I really know how to tell you how to do that, but I'll say that Dave, I mean, he's a very successful astronomer. Anyone who knows him or knows of him. So most people know him because he discovered the first Kuiper Belt object after Pluto, and basically kind of, you know, opened up the gates to, you know, now there are hundreds of thousands known, I guess. But he's also done stuff on comets and Jovian satellites, and he's just interested in lots of different things. And I've had conversations in his office about how rainbows are made. So it's, I think that maybe helps him do what he does, because he has a lot of information in his head, and you know, is able to make connections sometimes that other people don't. So he likes to say something, I'm going to paraphrase, but something like, if you always do what other people are doing, you're never going to find anything new. So he likes to do things that other people aren't doing. So I don't want to talk too much. So anyway, so today he's going to talk about comet science. So so this will kind of run the whole range of comets, which many of you maybe don't know too much about. So with that, I will turn it over to Dave.
Okay, thank you. So first of all, can you hear me? Yes? Okay. So this is about comet science. And it's going to be a talk made for people who are not working on comets, and maybe you're not even working in astronomy. So I'll assume that you have some interest in the subject, and hopefully give you an interest if you don't have one to begin with. So let's just do it. The objective of the talk is this. I want to give a big picture overview of the work that's going on comets right now. Comets are very active subjects of study. And the reasons are many and varied, but the main reason is that comets are bodies which formed in the beginning of the solar system and have remained at very low temperatures ever since. So nothing has happened to them. They preserve material from the beginning of the solar system, or at least that's what we hope is the case. I'll give you an introduction. We'll talk about these two main reservoirs, the Oort cloud and the Kuiper Belt. I'm going to cut that out of the talk because during lunch I was asked to talk about the Rosetta mission, the spacecraft that's gone to a comet. So I'll add a different bit in at the end there. So first of all, introduction to the comets. Let's have a really broad introduction. So you know, about 110 years ago, a person called James Jeans observed that the interstellar medium, the gas between the stars, is subject to an instability. So he did this thought experiment. He said if you get a balloon and squeeze the balloon, you increase the pressure in the balloon. When you let go, the balloon will bounce back to its original size. And if you do that with a bigger balloon, the same thing happens. You squeeze the balloon, the volume goes down, the pressure goes up. When you let go, the balloon will spring back to its original size. But if you do that for a really, really, really large balloon, when you let go, you squeeze it and you let go, it doesn't spring back to its original size. It continues to collapse. And it continues to collapse because of gravity. When you squeeze the balloon, if it's really, really big, you pass a critical threshold at which gravity can overtake the dynamics of the balloon and resist the effects of gas pressure, which are trying to make the balloon expand. So people simulate things like that numerically. And this is a nice example of a cloud of 500 solar masses of stuff, initially at 10 Kelvin, collapsing under its own weight, basically. It's a gene's mass, more than a gene's mass of material. And what you see is on this time scale, something like 1 million years, the collapsing cloud densifies, so yellow is dense material and hot material, and forms these filaments and strands and strings. And then these little bright points begin to appear here, first of all, and then there's another location over here where we see more of them. Those are the things that we call stars. So those are places where the interstellar medium has been squashed enough by its own gravity to become dense enough and hot enough for nuclear fusion to begin. So these are stars spitting out from star formation cluster centers. And so simulations like this explain something that you can see with your eye in the sky, which is that the stars tend to form in groups, not singly, not isolated, but in groups of typically thousands of stars altogether. And so this is a simulation by Matthew Bate, who's simulating kind of a person who likes to, as most N-body people do, rotate their models and look at them from different angles. And ooh. Anyway, you get the point. So stars form in clusters; they don't form alone. And that's important because our sun is a star, and we infer from things like this the sun probably formed in a cluster. So what formed from this collapsing cloud? Well, the star formed, but because of angular momentum, the collapsing material is also spun into a disk, a flattened disk. And the disk has a strong radial density gradient and a strong radial temperature gradient. And different things form in the disk. So in the middle parts of the disk, we have what we call the terrestrial planets, the rocky planets. They formed inside this location called the snow line. Inside the snow line, water can only exist as a gas, not as ice. And so the terrestrial planets, Mercury, Venus, Earth, Mars, the Moon, and some of the asteroids, basically are rocks. They don't have a big ice component in them because the ice didn't exist. It was a gas in the beginning because it was too hot near the sun. We know a lot about the terrestrial planets because we live on a terrestrial planet and we've sent spacecraft to all the other terrestrial planets. And so I'm not going to talk about those today. The giant planets, Jupiter, Saturn, Uranus, and Neptune, these things in the background, these are all to scale, by the way, are totally different. They're mostly made of gas. Jupiter and Saturn are mostly hydrogen and helium, just like the sun. Uranus and Neptune have many heavier molecules. And they formed in a different way. We're not completely sure how they formed, but most likely they formed by a process analogous to the way a raindrop forms. So a raindrop forms when water sticks onto a condensation nucleus. And the condensation nucleus absorbs some of the initial free energy of the molecule and allows the drop to grow. Condensation nucleus is a piece of salt, a piece of dirt, a piece of dust, or a bacterium, typically in the middle of a raindrop. In the case of these giant planets, the condensation nucleus is a terrestrial planet, essentially. So we think the giants have terrestrial planets inside. We know quite a lot about the giant planets, but not as much as the terrestrials because we don't live on one, and we have sent a spacecraft around this one and around this one. These we've only flown past with spacecraft, so we have very little information. But we still know more about them than we know about the comets, and so I want to focus in this talk on the comets in these two reservoirs. And just because these are pretty pictures, I thought I would put the pretty pictures there for you to see. Again, that's to scale. That's the Earth is Jupiter 11 times, Saturn 10 times, and so on. All right, the comets. So comets have been known to people probably before, certainly before the invention of writing, probably before the invention of language. And in fact, you know, dogs probably can see comets. They don't know what they are. Maybe they don't know what they are. But they're sometimes prominent features in the sky. I wish we could talk to dogs to find out what they know about comets. Maybe they know more than we do. So there are a number of things that you can learn quite simply by looking at comets. I don't know if this is cutting out or my voice is cutting out. So we have a couple of things. First of all, when you look at a comet, you're seeing a body which is losing mass. And we can measure the rate of loss of mass. And in a comet like this, maybe I'll hold this microphone. In a comet like this, the mass is being lost at maybe 1 ton or several tons per second, a few thousand kilograms per second. So that's easy to measure. We also know that the mass comes from a little solid body in the middle, down here at the head, that's probably about 1 kilometer across. And so it's straightforward to estimate the mass of this thing in the middle. The mass divided by the mass loss rate gives you the lifetime of the body. The lifetime of a comet to mass loss is like 10,000 years, 20,000 years, 30,000 years. It's very, very short compared to any astronomical timescale. So when you see comets, you know that they're not going to last long. You know that they're recent arrivals in the inner solar system. They're losing mass because of sublimation. Ice is turning into gas, blowing out material. And you know that they came from somewhere else. So just by looking, you can make this observation, and you can infer that they must have come from some other place, presumably a cold place, where they don't lose mass. And so we know of these 2 places, the Oort cloud and the Kuiper belt, by looking at the orbits of comets. It turns out if you divide the orbits into long period and short period, and the difference is simply whether the period is long or short compared to 100 or 200 years, what you find is that long period comets have very, very elliptical orbits that go from near the planets all the way out, many, many thousands, sometimes tens of thousands of AU, to vast distances. And those orbits have random orientations relative to the Earth. So they're an isotropic distribution. You have equal numbers of comets in the northern hemisphere and the southern hemisphere, retrograde, prograde. It's an isotropic distribution of comets. So the Oort cloud is a spherical feature surrounding the sun that supplies comets to the so-called long period population. So the Oort cloud is something we'll talk about in just a moment. The comets with periods less than a couple hundred years are quite different dynamically. They have short periods, of course. They have small inclinations. They are aware, they know about the plane of the solar system, and they have small eccentricities. Instead of going out to very large distances, they mostly go out to about the distance of Jupiter, which is 5 times the Earth-Sun distance, 5 AUs. So it's quite amazing. Just by looking at the comets, you can make this inference that the comets must come from somewhere else. They're supplied from a cold place. And then by making this observation, short and long period comets are different, you can figure out there are 2 source regions, 2 reservoirs for the comets, Kuiper belt and the Oort cloud. So here's this disk that formed around the young sun. There's the young sun. The disk has a scale, we think, of a few hundred AU, maybe a bit bigger. The time scale for the growth of a planet, if it's a terrestrial planet, occurs when dust grains stick together to make a bigger dust grain. They stick together to make a grain of sand, then a pebble, then a boulder, all the way up to planets. That time scale increases with the distance from the star, something like to the 3rd power, maybe 3.5. So a very strong increase with distance. So planet formation is rapid in the middle parts of this disk, and it's very, very slow in the outer parts of the disk. And so the planets are in here, and the comets, we think, formed a little bit in here, but mostly out here. So we're interested in the region that still looks dusty in this diagram. The outer regions, the cold places in this disk. Now then, astronomers and like most scientists, like to classify things, and they like to put things in boxes, although that's often not a reasonable thing to do, but we still do it. So we now see all these connections between different populations in the solar system that I don't need to talk about too much. The point of this diagram is simply to tell you there's lots of boxes. And in the past, planetary astronomers studied the things in these boxes as though they had no connection to each other whatsoever. It's like, I'm going to study you, and you have no connection to you, and you're not the same species, nothing. I'm not aware of any connection. Bang. Nowadays we know that there are strong connections. So we know that these objects are all connected up to the Kuiper belt, and these objects are all connected up to the Oort cloud. So we've just in the last 20 years, identified these connections between all sorts of weird, freakish things in the solar system that previously had no known connection. So, what we've got, in fact, now is three reservoirs for the comets. We've got the Oort cloud that was identified by Jan Oort in 1950. The Oort cloud is vast. It is about 50,000 AUs in radius. It extends out roughly 1/4 of the way to the nearest stars. So it's a vast population. And it contains hundreds of billions, maybe up to 1 trillion comets, bigger than a kilometer or so. Quite a lot of objects, most of which we have never seen and will never see because things are so far away in the Oort cloud that we can't see them. We only see them when they fall into the inner solar system. We have a Kuiper belt that was discovered in 1992, which basically begins at Neptune's orbit and goes out to many thousands of AUs and beyond. And the Kuiper belt contains maybe 1 billion, maybe 10 billion objects bigger than a kilometer, something like that. And we have this third population, which Henry discovered as part of his thesis in 2006, which seems to include some comets amongst the asteroids between Mars and Jupiter. So there's this strange third population that doesn't seem to derive from either of these other populations. It's an independent source about which I will not talk today, but it exists. Okay, Oort cloud first. So Jan Oort inferred the existence of Oort cloud from this diagram, basically. This is the orbital energy, so it's the 1 divided by the semi-major axis of the orbit. Okay, so 0 means an orbit which is not bound to the sun. Equivalently, it means a parabolic trajectory. Positive numbers mean that the comet is gravitationally bound to the sun and the orbit is an ellipse. And negative numbers mean that the comet is unbound and it moves relative to the sun on a hyperbolic orbit. So first of all, there are very, very few hyperbolic comets, okay? And those few hyperbolic comets are barely hyperbolic. It's almost like a parabola, and maybe some of these are due to measurement errors, others are due to deflections by the planets before these things were detected. No strongly hyperbolic comets are known. And in particular, we could say from this diagram that no interstellar comets have been detected. So an interstellar comet would come through with a large relative velocity, and on this diagram, it would plot over there, somewhere on the other side of this building, over there. So we don't see any comets like that. We don't see any unbound comets. Everything is attached to the sun. Talk about that in a moment. So that was Oort's first observation. He said, well, this must mean there's a cloud of comets attached to the sun. We already know the cloud is isotropic, so he said the cloud is like a sphere. The next one is very subtle, but very important. There is a very narrow peak near zero binding energy, so nearly parabolic, but just slightly to the right. So strongly elliptical, slightly bound, strongly elliptical orbits of comets. He made the important observation that the width of this peak is very narrow. And in particular, the peak is more narrow than you would expect if the comets in the peak had been through the solar systems many times before. So you can imagine dropping a comet from infinity. If there were only a sun, one sun, the comet would go straight in along the line of centers and hit the sun. But the sun has a planetary system. To a first approximation, the solar system is Jupiter. So you can imagine dropping a comet into a Sun-Jupiter system. As the comet falls in, it'll be going towards the sun, but it will feel a slight deflection to the side by Jupiter. That will change the binding energy of the comet a little bit. And Oort's observation is that this peak is sufficiently narrow that the comets in the peak cannot have fallen into the solar system many times before. Maybe twice before, but not 10 times, not 20 times, not 100 times, not 1,000 times before. So these comets are arriving in the solar system for the first time, and they probably are being kicked in by the gravity of passing stars. So they're out at 10,000 AU, 50,000 AU, perturbations kick them in, they fall into the inner solar system, and we say, aha, that's a new comet. So that's the essence of Oort's cloud. The trouble is that Oort's model actually doesn't fit the next observation, which is, well, there are a lot of comets in here relative to the comets in here. So presumably these are first arrivals from the Oort cloud, and these are like 10th arrivals and 50th and 100th arrivals. In Oort's model, these objects should be up here. And so the observation is that there are not enough comets making return visits to the sun after they've been through one time. So to solve that problem, Oort took his dynamical model and added to it a parameter, basically a fake parameter, a fudge parameter, called the fading parameter. He said, well, for some reason that I don't really understand, comets coming through the solar system for the first time are extra bright, extra visible, so we see them all. And then the next time through, they're intrinsically fainted. They've lost some cross-section. They've lost some dust somehow, and we can't see them so well. So he introduced this fading parameter into his model, and we still don't really know what that fading parameter is. People have looked at it in various ways. Here's what the model would predict without fading, and here's what we see. So there are different ways to parameterize the fading, but we don't have a mechanism. So the ugly truth is that it's actually a cheat. It's a model cheat. But Oort is such a highly regarded astronomer. He's dead now, but he's still a very highly regarded astronomer that we don't say he cheated. We say that he discovered the fading parameter, although we don't really know what that fading parameter is. Yeah, it's the same kind of thing. Yeah.
There's some experimental evidence for that.
We'll come back to that. Yeah. He suggested, he called it interstellar frosting. He said, when a comet's in the interstellar, out there in the Oort cloud, subject to the interstellar medium, very volatile materials floating by can stick on the surface. And then the first time it comes into the sun, they all evaporate. Interstellar frosting. Anyway, okay, so you get the point. There is this problem called the fading parameter problem. So here are the parameters. It's about 50,000 AUs in radius. The orbital speed, the orbit speed of the Earth is 30 kilometers per second. The Kepler speed for something out there is about 100 meters per second. Because it's so slow, the gravity of passing stars can deflect objects. And so we think the Oort cloud began as more like a disk, but was distorted into a sphere by the perturbations from passing stars, which are random, integrated over time. Here's the probable population. The mass is very uncertain because we don't really know the average size of cometary nuclei, but it's at least an Earth mass and maybe 10 Earth masses of comets in the Oort cloud. And the time scale for isotropizing, for making it a spherical cloud by external perturbations, is 1 billion years, so about a quarter of the age of the solar system. Okay, so there are many interesting things with the Oort cloud. The trouble is that we cannot observe the Oort cloud objects directly. Only when they've been kicked into the inner solar system can we even see them. Otherwise, we have to infer their existence. We know that they couldn't possibly form in the Oort cloud. So the Oort cloud is so big and the density is so low that no two comets ever meet. Two dust particles in the Oort cloud never meet. There are no collisions, so nothing can grow there. So we think that the Oort cloud comets formed actually in the disk close to the sun, probably in the vicinity of the giant planets. And if they were not eaten by the giant planets to grow their cores, they were scattered by the giant planets out of the solar system. They were basically given the boot, and off they go, faster than the escape speed, leaving the solar system. The trouble is that it's very difficult to launch something, it's actually impossible to launch something with the right velocity to put it into orbit. So I have a little demo, it's based on a coin, and because I'm not from Taiwan, I have no idea what the coin is. So if I want to throw this coin up and just touch the ceiling, let me see if I can do that. Oh, nope, it fell too low. So I'll go a little faster, and if I get it just right, I'll just touch the ceiling. Still didn't work. And so I'll just try one more time. I know it's going to take a long time to get this right. I'll just try one more time just to touch the ceiling.
Yes.
It touched it, but it touched it too fast. It didn't just kiss the ceiling, it hit it hard. So imagine I'm a planet trying to eject comets. Most of the things I eject actually will either fall back, in which case they can be ejected again, or they'll leave faster than the escape speed. And that's the case. So we think the efficiency for capturing objects into the Oort cloud is very small, 1% to 10%. And most of them left. Almost everything that was ejected left. And it's off floating in the interstellar medium now among the stars. So, what would give rise to this efficiency? Well, on the way out, it takes 10 million years to go out to the Oort cloud. On the way out, many stars pass by, and the gravity of those stars can deflect the departing comets and circularize their orbits. So that's a model result. It's probably roughly correct. But what it means is, if there's one Earth mass in the Oort cloud now, somewhere between 10 and 100 Earth masses have to be ejected to get that one Earth mass captured. So the sun formed in a cluster, as we saw from the initial movie. It's been pointed out recently that when the sun was in the cluster, it could share comets with other stars. And so in fact, it may be that some long period comets, or many or all comets, were formed around other stars and then swapped over to us in these early phases. There is an inner Oort cloud, which is essentially unobservable because it's close enough to the sun to be immune to perturbations from passing stars, unlike the outer Oort cloud of 50,000 AU, where the gravity of passing stars is important. So these are all things that people are interested in and working on. We're sure of the existence of the Oort cloud, but we don't know a lot about it beyond its existence. Very recently, you might have read some reports of objects that have been discovered with large orbits. So basically, people are looking at the Kuiper belt and seeing things that have a relatively large orbit compared to the Kuiper belt distances, which are in here. And there's this observation that the angular distribution of the orbital elements is unexpected. So all of these objects have argument of perihelion, something like 40 degrees on this plot, plus or minus a large amount. And one suggested interpretation for this is that there's a planet not too far beyond the known planetary system that is basically channeling the orbits of these bodies, so they have to come into the solar system in a particular way. So it's possible that these are inner Oort cloud objects being deflected by an unknown, unseen planet. Although I think that explanation is not secure at all. It's a possibility. That's a result from Nature or somewhere this year by these people. Okay, and by the way, if you took the Earth and moved it away until it were so faint that it couldn't be seen by any existing telescope, that distance would be something like 1,000 AU. And if you did the same to Jupiter, you could move it to 4,000 AU before it would become too faint to see. Okay, so let's do Kuiper belt. So Kuiper belt is this ring beyond Neptune. It's the place where the short period comets come from, as we said. And then here's a Rosetta picture. We'll come back to these in just a moment. So the first importance of Kuiper belt is that it's the source of the short period comets. The Kuiper belt, we now know, has quite a lot of objects in it. We have 1,600 known Kuiper belt objects. These are the giant planet orbits here. These are the actual KBOs. It's the heavily populated part is something like 100 AUs across. In the middle, there's a more artistic diagram of the thing, totally unrealistic, but artistic. And the great thing and special thing about Kuiper belt is Kuiper belt objects are near enough that we could see them directly. That's the big difference between the Oort cloud and Kuiper belt. We can actually observe objects in the Kuiper belt with existing telescopes. We can't do that. Or maybe we can barely do that now for some